What is the engine behind the Internet? As discussed in the introduction, what makes the Internet work is the global telecommunications system that allows data traveling at the speed of light. The science and engineering behind the circuits in Lab 6 have been historically driven by the need of communication technologies. Hence, communication engineering is the theme for our studies. Specifically, we will show that Lab 6 circuits have applications in what known as modulation and demodulation. In order for information to be sent around, it must be carried by physical entities, which are principally electromagnetic waves. We are familiar with radio waves, which are electromagnetic waves in the megahertz to hundreds of megahertz range for radio and TV. Frequency is like seats on an airplane. More seats carry more passengers. The higher the frequency, the higher is the information carrying capacity. More important for data communications are microwaves, from 2.4 or 5 GHz for the ubiquitous Wi-Fi, up to tens of gigahertz for advanced mobile communications network. Ultimately, all aggregated data from local area networks are carried by 200 terahertz light waves in millions of miles of optical fibers spanning around the globe, which is truly the engine of the Internet. We are familiar with information, data, represented with bits and bytes. To be carried by a wave, however, the data must be imprinted onto the wave properties, like passengers, who must get into the seats on an airplane to start a flight. This process for data is called modulation. Demodulation is the opposite of modulation, like a passenger to get off a plane at a destination. Modulation and demodulation are often abbreviated as modem, to denote an electronic device performing this function. The bandpass filter of Lab 6 is a typical part of a modem. The three properties of a wave carrier, amplitude, frequency, and phase, are like different sections of an airplane cabin for passengers. Each can be modulated to carry the data. The previous demonstration shows amplitude modulation, like in AM radio. Here, we will do some highly simplistic conceptual demonstration of frequency modulation, or FM. In addition, Lab 6 circuits can be used to illustrate the concept of heterodyne, which can provide a foundation for one's future learning of coherent detection and high-capacity modulation techniques, such as quadratures used in phase modulation or phase shift keying. If you are familiar with amplitude modulation, you can skip this part. This review is to benefit those who have not seen the other presentations and wish a quick demonstration on the concept of carrier and signal modulation. The top trace shows a square wave signal that amplitude modulates a sinusoidal carrier in the on-off format. The bottom graph shows its Fourier spectrum, with a peak at the carrier frequency of 9.1 kHz. The amplitude modulation is turned off, showing a pure carrier without any data. Its Fourier is just a single peak. Turning on AM shows the modulated signal, and its Fourier spectrum shows the side bands at the data rate frequency. If you have not learned Fourier transform, do not be concerned. Real data, real signals have random waveform. For the sake of demonstration, the following shows other simple waveform modulations. The bottom blue trace is actually the demodulated signal, showing the restored original waveforms. This demonstration illustrates the concept of signal modulation, represented by the top trace, and demodulation, the bottom trace. The previous demonstration, however, does not explain why data are modulated, only to be demodulated later. Why not sending data in the original form? The reason is demonstrated here. No communication channel is without noises, like statics on the radio. and there are always multiple streams of data, like many radio stations. For illustration, the scope yellow trace in the top graph shows data AM signals being mixed up with another interference signal. The bottom Fourier spectrum, yellow, shows two peaks. The left side one indicates the modulation frequency of the desired data, and right side peak indicates that of the interference. Modulation gives the data a distinctive frequency that can be selected, while all interferences are excluded. The blue trace, top, shows the demodulated signal, which shows the desired data in the original form, but not the interference data. In the follow, the signal and the interference are alternately turned on and off as indicated in the top right box. When the signal is off, its Fourier peak disappeared, and the blue trace, top, shows only the desired data being received, and no interference data seen. When the interference is off, the demodulated signal blue trace is shown to faithfully represent the data. The roles of Lab 6 circuits are shown here. The signal with noises and interferences is input into successive bandpass filters, and lastly demodulated to output the restored signal. Next, let's consider frequency modulation. In frequency modulation, the amplitude of the carrier is not varied to represent the data, but only its frequency. On the scope yellow trace in the top graph, the carrier can be seen changing frequency, and in the bottom graph, its Fourier peak can be seen shifting left and right, in proportion with the frequency modulation amplitude. The frequency modulation rate, that is, how fast it changes, is the data transmission rate, while the frequency modulation amplitude indicates how much it changes. The larger the frequency changes, the easier to see, which entails the higher resolution of the data level. Sure, but all advantages come with costs, as we will see. How much the frequency changes, or FM amplitude or index, is like how big an airplane is. A large airplane can carry more passengers, but at the cost of more space and higher operational expenditures. Large FM amplitude will make the channel bandwidth larger, which can have a higher data rate. In the frequency space, as discussed in other demonstrations, bandwidth is a prime real estate. Larger bandwidth incurs higher cost. Hence, the data rate should be at maximum allowed level, given the FM bandwidth and signal-to-noise ratio, like an airplane cramming as many passengers as possible. However, the data rate shown here is very low for the ease of visualization. Like the AM demonstration, different waveforms are used for FM. For square wave, the jumping of the frequency left and right as evidenced in the Fourier spectrum of the bottom graph is called frequency shift keying. For triangle or ramp, the frequency is said to be chirping, which is quite relevant for some radar applications, known as the chirped radar. Sine wave can be used to evaluate an FM system frequency response. Lab 6 band pass filter circuit, as shown here with its Bode plot, can actually be used in a highly simplistic way to demonstrate the demodulation of an FM signal. The bottom left graph shows the frequency response on the linear scale. The small rectangle shows a frequency range where a change of frequency can result in a change of the passing signal amplitude. Hence, an FM signal in that range will have its output amplitude proportional to the FM amplitude. In other words, the FM signal is converted, or demodulated into an AM signal. Consider a pure carrier at 11.5 kHz. The Fourier spectrum at the bottom shows a single line. Frequency modulation is applied to the carrier. As illustrated in the animation graphics on the lower left, the carrier output amplitude, the blue trace, moves up and down correspondingly to the Fourier spectral line moving side to side. How fast the modulation should be is determined by the data rate. In the follow, observe the modulation rate being slowly increased, and the effect on the Fourier spectrum. The Fourier spectral line is broadened, or its bandwidth increases as it includes the modulation rate. A more important factor on the bandwidth is the modulation amplitude. It widens as the modulation amplitude is increased. Waveform, or modulation format, also affects the bandwidth as shown. Frequency shift keying, or square wave costs the highest bandwidth as evidenced, which is true for any modulation with discontinuous sharp edges. Sine wave is the most economical modulation for the bandwidth, and it can be used to study the frequency response of this FM system. The previous technique of demodulation is of the passive type. It has the advantage of simplicity, but also some disadvantages. A more common technique is active demodulation using heterodyne, or nonlinear mixing, also known as coherent detection. The Lab 6 circuit that can be used for this demonstration is the adder as shown. It simply adds two signals together. The top graph shows the scope traces of two input signals. They start out with the same frequency. The Fourier spectrum at the bottom shows overlapped lines. The frequency of the second signal, blue, is varied, as evidenced in the Fourier spectrum, and the two peaks are no longer overlapped. Next, the output of the adder circuit, that is, the sum of the yellow and blue signals, is shown. It has the typical waveform known as beat. The frequency of the envelope of the beat signal is the difference of the two signal frequencies. As the frequency of the second signal is varied, the beat frequency also varies, and the Fourier spectrum in the bottom right graph correspondingly shows how close, or how far apart the two frequencies are. However, the Fourier spectrum tells a story more complex than it appears. In principle, there should be only two frequencies, F1 and F2. But it is evidenced that there are other frequencies, F1 plus F1 minus F2, and F2 plus F2 minus F1. These are caused by nonlinear mixing, which was mentioned previously in the context of coherent detection and heterodyne. Why do they appear here? Because the op-amp is not perfectly linear. In fact, no circuit element is perfectly linear. The new frequencies involve three terms of the input frequencies, hence, known as third-order nonlinearity. They are ubiquitous in all oscillatory phenomena in nature, in RF waves, light waves, seismic, mechanical vibrations, sounds, including our vocal cords, not just in circuits, and known as Stokes and anti-Stokes components. More relevant to our demonstration of heterodyne is second-order nonlinearity, which is also seen in the Fourier spectrum. The peaks labeled second-order harmonics on the right side are called second-order, because it involves two terms of the frequencies. Of particular interest is the F1 plus F2 term. Is there a corresponding f2-f1 term? The answer is yes, and it is precisely the main term of interest in the following presentation. Consider the Lab 6 circuit. The adder beat signal is input into the bandpass filter, although this is not necessary, because no noise or interference is added for simulation. However, it is a matter of common practice that the signal is always filtered with a bandpass, and also it is convenient to use the circuit as is. The filter output is input into a diode, which is used as a rectifier to demodulate a signal in other demonstrations. However, here it is used as a nonlinear mixer. The adder output, sent through the bandpass filter, then coupled into a diode. The scope yellow trace is the output of the bandpass filter, showing essentially the original beat signal. Its Fourier spectrum consists of two main components. The nonlinear components on the sides are more than 40 dB, that is, 10,000 times lower power compared to the main components. The nonlinear mixing components can be identified by simply switching off each signal alternately. The components that exist only with both signals are the nonlinear mixing components. As evidenced, there are only a few nonlinear mixing components, and their power are relatively low. Now, the output of the diode will be connected to the scope for observation. The property of the diode that makes it nonlinear is quite simple as shown. It simply truncates the negative part of the signal. It is evidenced by comparing the Fourier spectrum of the yellow trace, which is the beat signal before the diode, and the Fourier spectrum of the blue trace, the signal after the diode, that there are many nonlinear mixing components, and that the power of many are significant, within an order of magnitude of the main components. Based on the Fourier components that exist only with both signals being on, it is apparent there are three main nonlinear mixing groups. A center group in the frequency range of the original signals is actually of no interest, because they are of third or higher order nonlinearity. A high frequency group involving the doubling and adding of the two main frequencies is also of no interest, because in real applications, they are non-existent because of too high frequency, outside the range of the mixing device, or the power is virtually non-detectable. The only group of practical use and of interest is the low frequency. A close-up of the low-frequency portion of the Fourier spectrum shows the main and only nonlinear mixing component of interest. It is the absolute of f2-f1 component, which is the heterodyne signal. The DC component, the line at zero frequency, is not a nonlinear mixing component, hence it is not desired and will be filtered out later. The selection of the desired heterodyne component, which is the absolute f2-f1 component, can be done in successive steps. The first step is to use a low-pass filter to block out all the high-frequency components. This is done by coupling the diode output into a low-pass filter circuit. The yellow trace is now the signal after the diode, which is input into the low-pass filter. The output of the low-pass filter is represented by the blue trace. From the comparison of their Fourier spectra, it is evident that the low-pass filter blocks all the high-frequency components as expected. The low-pass filter output, the blue trace signal, contains the desired heterodyne component. The second-order harmonic is more than 20 dB lower and not of concern. The next step is to remove the DC component. To remove the DC component, a very simple passive RC circuit is used for AC coupling the low-pass filter output. The DC component is removed, and the signal now is the true heterodyne mixing component. It can be verified once more, that the component requires both carriers to exist as demonstrated, with the two carriers alternately turned on and off. The frequency modulation can now be turned on to simulate data, and the heterodyne signal carries the data signal. Demodulation can be performed as previously, but on a much lower frequency range. Since the heterodyne frequency is very low compared to that of the carrier, small relative FM amplitude on the carrier, for example, a few tenths of a percent, becomes large on the heterodyne signal, facilitating FM demodulation. The objective of the previous demonstration is to maximally utilize the circuits of Lab 6 for educational purpose. Although strictly speaking, the diode is not a nonlinear mixer, it is useful for the simulation and introduction the concept. In the theme of communications, what we learn is a part of a common technique of modulation and demodulation, known as quadrature. One of the two carriers in the previous demonstration assumes the role of local oscillator, the other assumes the role of data carrier. In practice, the data are modulated in amplitude or in phase for quadrature amplitude modulation or quadrature phase shift keying. The point is not about learning the topics that are not within the scope of this course, but to appreciate the function of the circuits that you built in the greater context of communication technology.